Hello, welcome to Understanding Power Electronics. In this video, we will see what constitutes steady state in power electronics. In a DC circuit with inductors and capacitors, the circuit will go through a transient before it reaches steady state. At steady state, the voltages and currents everywhere in the circuit will be constant. Whereas this is not so in the transient period, the values will be changing until they reach constant values in steady state. Likewise, in an AC circuit, there will be a transient period before the AC voltage and current waveforms everywhere settle down. That is the steady state operation in AC. Likewise, in a power electronic circuit, the system will go through a transient interval before reaching steady state. In this video, we will see what constitutes steady state in power electronics using a simple example of a buck converter and how the circuit goes through a transient before reaches steady state, and compare this with an example of a DC circuit and see where they are similar and where they are different. With this in mind, let's get started. First, we will consider a simple LR circuit fed by a DC voltage source. The inductance and the resistance and the DC voltage source are in series. The inductor value is taken to be 200 microhenry and the resistance value is taken to be 10 ohms. Then the time constant will be 200 divided by R. Tau is the time constant, which is 20 microsecond. If the time constant is a large value, then you know that the response will be slow. If the time constant is a small value, then the response will be faster. So time constant determines the speed of response of the circuit. We wish to solve this circuit. Solving this circuit in this case means finding the current and the voltages everywhere. Let us find the current. The current IL, which is the inductor current, and the loop current. We do this by applying Kirchhoff's voltage law to this circuit. So the voltage across the inductor, the voltage across the resistance, the voltage across the source, if they are all added together, taking their signs into proper account, it should add up to 0. The voltage across the inductor is given by L di by dt, where di by dt is the rate of change of the current, dIL by dt, rate of change of current. That is the induced voltage in the inductor, plus RIL, the voltage across the resistance, that equals VDC. The initial current is taken to be a IL0, some constant value. At time equal to 0, we assume that the inductor has a current of IL0 already. Now this equation can be solved in various different ways. You can use Laplace transform, you can use homogeneous solution and particular solution method. So I will give you the final solution in here, which I assume many of you will know it. IL, which is a function of time, the inductor current, that is given by IL0, the initial value of the current, minus VDC by R times e power minus t time function divided by tau, where tau is of course the time constant, plus VDC by R. This is the solution which electrical engineering students will be aware of. Now, let us consider three different cases, three different values of VDC and IL0. So the first case that we will consider is VDC equal to 25 volts and IL0 is equal to 0 amperes. So since IL0 is 0 amperes, we can neglect this term and VDC by R will become common. We will do that manipulation here. We can take out the VDC by R common. So VDC by R times 1 minus e power minus t by tau. Now we can substitute the values for VDC, R and tau. You will get the solution IL for this particular case 2.5 times 1 minus e power minus 50,000. 50,000 is 1 by tau t e power minus 50,000 t ampere. Notice that when t is 0, e power minus 50,000 times 0, that will be 1. So 1 minus 1 is 0. So IL will be 0. So initial current is 0 as we expect. IL0 is 0. When t is large, then this term will become 0 or close to 0. When this close to 0, IL will reach 2.5 amperes. T need not be very large. Even when t equal to 10 times tau value is the time constant value, that is 200 microsecond, or even 5 times tau, that is 100 microsecond, you will find that IL would have already reached very close to 2.5 amperes. So it rapidly goes to 2.5 amperes. Let's plot this result. This is the x-axis, of course, the time axis in microsecond, and the y-axis is the current IL. And the plot is 1 minus exponential decay curve. You can see that after an initial variation, it reaches a constant value, which is of course the steady state, and that is equal to 2.5 amperes. So that is the steady state, and the initial part where it is reaching towards 2.5 amperes, that is your transient. So in a DC circuit case, it's fairly straightforward. You have a transient part and then you have the steady state part. Suppose I am analyzing this DC circuit and I am only interested in the steady state value. I am not interested in the transient value. I want only the steady state value. Then I do not have to go through all this derivation. I don't have to write the differential equation. I don't have to do all this. How do I do that? Under steady state conditions, the inductor current is constant. So di by dt is 0. So LdI by dt, which is the inductor voltage, that will also be 0. We are aware of that. So because that is 0, this term goes off. So only RIL remains. RIL equals VDC. So IL steady state is VDC by R, which is 25 volts divided by 10 ohms, which is 2.5 amperes. So we can directly get the steady state by assuming all the inductor voltages across the inductors are 0, or that inductor is a short. That's how in the first year electrical engineering we learned that under steady state, DC steady state, inductor can be treated as a short. Likewise, if you have a capacitor in the circuit, under steady state the capacitor current will be 0. So the capacitor may be treated as an open circuit. So by treating all circuit capacitors as open circuit and all circuit inductors as short circuit, and then solving the resulting circuit, I can find the DC steady state value without going through the differential equation route. So the intention here is to find the steady state directly. So please remember that. Now I am going to consider two more cases with the same circuit and with the same solution. The reason why we are doing this is these three cases will be useful to us while we are analyzing the power electronic converter a little while later. So the next case is VDC is 25 volts and IL0 is not 0 amperes but instead 1.1 ampere. So none of the terms here goes to 0. Take that equation, plug in all the values. The equation becomes IL minus 1.4 e power minus 50,000 t plus 2.5 amperes. So this is the solution in this case. I have taken the initial current 1.1 ampere, arbitrarily. So we can plot this. The red curve shows that it starts from 1.1 ampere and goes to 2.15 ampere. The steady state is still the same. So when t is very large, that is 5 tau or 10 tau value or higher, then this first term becomes 0. So IL will go to 2.5 amperes. The starting value is 1.1 ampere because the initial current is 1.1 ampere. So if I put t equal to 0, this term e power minus 50,000 t becomes 1 minus 1.4 plus 2.5 is 1.1 ampere. So starting from 1.1 ampere, the current quickly builds up to 2.5 ampere. So this is case 2. Here also this is the steady state part and this is the transient part. Now we will see a third case. In case 3, the VDC itself is made 0 while IL0 is at 1.1 ampere. So the VDC source becomes 0, or you can treat that part as a short circuit as here. So the inductor and the resistance are connected together and they form a loop. The inductor still has an initial current of 1.1 ampere due to some previous operation. So we will once again take that equation, our solution equation. IL0 is 1.1 ampere, VDC by R is 0, VDC by R here also is 0. So the solution becomes 1.1 e power minus 50,000 t. So it starts from a value of 1.1 and quickly goes to 0 as time progresses. So the initial value is 1.1 ampere and the steady state value is 0 amperes here. So this is the steady state value, this is the transient part. Now to summarize the three cases. Case 1 is 25 volts VDC and the initial current is 0 amperes. And starting from 0, the current goes to 2.5 amperes steady state value. Case 2, VDC is 25 volts, IL0 it starts from a current of 1.1 ampere, the initial current. So from 1.1 ampere, it quickly builds up to 2.5 amperes. And case 3, as we saw, VDC itself is 0 volts, IL0 initial current is 1.1 ampere. So the current starts at 1.1 ampere but decays to 0 ampere. So you have three cases here. In all the cases, this part here is the steady state part and this part here is the transient part. Again, as I pointed out here, we can get the steady state value without going through the differential equation route. Directly we can obtain it. In a similar way, if you do the AC analysis, sinusoidal AC analysis of linear circuits, which you would have done, that is resistance, inductance and capacitance with a single sinusoidal source, it goes through a transient. The voltages and currents and all the different nodes of the circuit will vary until it reaches a steady state. Under steady state, the AC voltages and the AC currents will be maintained. Of course, they are sinusoidal, but the values, the RMS values, the peak values, etc., the frequency, everything is maintained. Again, we can set up the differential equation and solve the AC circuits to reach the steady state solution, like we did for the DC case here. But the AC analysis in AC circuits allows you, by using the J omega technique and all that, by using the phasor technique, to directly find out the current and voltage values under steady state. So we would like to do a similar thing in power electronics, as I will point out later. First we will see what happens in a power electronic circuit, and we will confirm that there is a transient, there is a steady state. That's what we will do next. Next we will see what steady state is in power electronics. Consider a basic DC-DC power converter. This is a DC-DC buck converter, also known as DC-DC chopper. I am considering a version with only an inductance for the filter rather than an inductance and a capacitor. This will make it easier to analyze in the manner in which I plan to analyze in this video. Let the inductor value L be equal to 200 microhenry and the resistance value R be equal to 10 ohms and the VDC, the voltage, be equal to 25 volts. You can see that these values are the same as what we had before for the simple DC circuit analysis. The switch is going to be switched on and off alternately, and let the frequency of the switching be 100 kilohertz. So the switch is switched on for a short interval, switched off for a short interval, and the process is continued. And this is the switch control waveform. And one on interval plus one off interval constitutes one switching period. One switching period equals 1 over the switching frequency, 10 microseconds. So the on interval plus the off interval will be 10 microseconds. The on interval divided by the period, that ratio we know is called duty cycle. That is T on by Ts is duty cycle. Let's say it is 0.6 for this example. With a duty cycle of 0.6, T on will be 6 microseconds and T off will be 4 microseconds. The output voltage, here the output voltage is the voltage across the resistance, or you can treat it as the load resistance. So output voltage average, that is VR average, will be duty cycle times VDC. Duty cycle is 0.6 times VDC 25 volts, that is 15 volts. The switch is switched on and off alternately. The voltage that is fed to the inductance and the resistance will switch between 25 volts and 0 volts. And the average voltage is duty cycle times VDC, that is 0.6 times 25 volts, that is 15 volts. With that load voltage value, we can find out what the load current will be, which is the average voltage here divided by the resistance. That is 15 volts divided by 10 ohms, and that will be 1.5 amperes. The average current in the load is the same as the average inductor current. Remember these values. The average output voltage across the resistance is 15 volts. The average inductor current is 1.5 amperes. We will use these values later in our discussion of this particular circuit and our discussion of transient and steady state operation of this particular converter. Now we will consider the step-down chopper, step-down DC-DC converter, and go through step by step how it starts, goes through an initial transient and reaches steady state. Initially the switch turns on. Let us assume that the switch is left on. Notice that the diode is reverse biased now. VDC, the positive terminal is here, negative terminal is here. So cathode is connected to the positive, anode is connected to the negative. So the diode is reverse biased. The diode will not conduct. So let's remove the diode. This is a DC circuit, LLR DC circuit fed by a DC source, the same circuit that we analyzed earlier. We have already solved this circuit and found the equation for IL, the inductor current. The initial current, when the converter starts, the inductor current is 0. So IL0 is 0. We know the values of VDC, R, tau, etc. So we can plug them in and we will get this equation, which is the same as equation for the case 1 that we obtained earlier. So this current we know will start from 0 amperes because IL0 is 0 amperes and go towards 2.5 amperes for DC steady state operation. So let's plot that curve. So this x-axis is time t in microseconds, y-axis is inductor current IL in amperes. Now if I plot this, it starts from 0 and goes to 2.5 amperes. But we are leaving this switch on only for 6 microseconds. So at 6 microseconds at this time, we are going to switch the switch off. So let us find the value of the inductor current when t is equal to 6 microseconds. So let's plug that value t is equal to 6 microseconds and calculate the value of IL. So IL at 6 microsecond is 0.648 amperes. You can check it out by doing the calculation. So this is 0.648 amperes. Just remember the diode is still there, so I'm bringing it back in. At this point, the switch is turned off. This shows that the switch is turned off at t equal to 6 microsecond. So let me turn off the switch here. So this part of the circuit is no longer effective. There is no current drawn from the DC source. There is no current flowing in the switch. So let me take off that part of the circuit. The inductor current now tries to go down because there is no DC voltage source. When the inductor current goes down, the voltage induced in the inductor will be opposite polarity. The indicated polarity here, plus on this side, minus on this side, is the reference polarity. So when the current is going down, the voltage induced will be opposite of the reference polarity. That means positive on this side and negative on this side. That induced voltage will overcome the voltage drop across the resistance, the IR voltage drop across the resistance, and the forward bias requirements of the diode. To make the diode conduct, the current will continue to flow in this manner. If you assume an ideal diode, the diode voltage drop is close to 0 or 0. So the inductance and the R resistance are looped together. Diode is practically a short. The initial inductor current is 0.648 amperes. This is the same case as case 3 seen earlier. Now you know that will give a solution that will take from 0.648 amperes down to 0 exponentially. The only difference is there it was occurring at t equal to 0. Here it occurs at t equal to 6 microseconds. You can start another time scale, let's say TA. So at t equal to 6 microseconds, I let TA be equal to 0 microsecond. So when t equal to 10 microsecond, TA is 4 microsecond, and so on. So then the equations that we got earlier, I can write it in terms of TA. TA in the new time scale that I am introducing here is t minus 6. When t equal to 6 microseconds, TA is 0. So the same equations that we derived earlier will apply here. Only thing is I will use TA. So this equation now is in terms of the time variable TA. That's about all. So IL is IL0, the initial current at TA equal to 0, which is 0.648 amperes. Essentially, the decaying curve, I'm just pushing it by 6 microseconds. IL equal to 0.648 e power minus 50,000 GA ampere. So if we plot this, it will be a decay of the current, exponential decay of the current, starting from t equal to 6 microseconds, starting at a value of 0.648 amperes and going down to a steady state. That is the steady state of this DC circuit, not the steady state of the power electronic circuit that we are talking about. So at t equal to 10, we are going to switch on the switch again. So let's find the inductor current at t equal to 10. So at TA equal to 4 microseconds, that corresponds to t equal to 10. I substitute TA equal to 4 here and I calculate this value, which is 0.531 amperes. Please do check it out. So this is 0.531. And don't forget, this part of the circuit is still there. So I'm just showing it here again. Now at t equal to 10 microseconds, corresponding to the inductor current of 0.531 ampere, I am going to switch on this switch again. So let's do that. So I'm going to switch it on and leave it on. Let me switch on this switch. So once the switch is on, the diode does not come into the picture. So I'm removing the diode and the current will flow in this manner. So you are having an LR circuit fed by a DC voltage with an initial inductor current of 0.531 amperes, some value. So this is exactly the same as case 2 earlier, only difference being now it occurs at time t equal to 10 microseconds and not at time t equal to 0 microseconds. Again, we introduce a new time scale. You can understand this idea in different ways. I'm just choosing to explain it this way. I'm making a new time scale TB, which starts at t equal to 10 microseconds and follows. So TB will be t minus 10 microseconds. Now I can write the equation that we got earlier for the LR circuit fed by a voltage source. Only I'm replacing the t with TB and then plugging in the values. ILO is 0.531 amperes, VDC is 25 volts and so on. I will get the equation for IL. This is similar to the case 2 current we got earlier. So this can be plotted. We know that the current will rise from 0.531 and exponentially it will go towards 2.5 amperes. Steady state. That is the steady state of this DC circuit. So let's plot that. So IL will follow now this curve. So IL starts from here, goes to 0.648 amperes. When you switch off, it comes down to 0.531 amperes. And then when you switch on again, it follows. It goes towards 2.5 amperes. Now you get the idea. We are going to switch off the switch at t equal to 16 microseconds or TB equal to 6 microseconds. So let's find the value of the IL at TB equal to 6 microseconds. So at TB equal to 6 microseconds, that is at t equal to 16 microseconds, I have to take the 6 microseconds value and substitute it here. So IL at t equal to 16 microseconds is 1.04 amperes. You can also check out this calculation. So this is 1.04 amperes. Remember, the diode is always there, so I am putting back the diode. Now the switch is turned off. We are just taking it through one step at a time. Switch on, switch off, switch on, switch off. How exactly the circuit goes through. If you are doing a simulation, that's exactly or similar to what a simulator will do, going through one time after another to see how the circuit and the system evolves. So at t equal to 16 microsecond, we switch off the switch. So let's show that the switch is turned off, and let's assume that the switch is turned off and it continues to be turned off. The current shifts to the freewheel diode. L and R circuit are in parallel with an initial current of 1.04 amperes. So you know that this will result in an exponential decay of current all the way down to 0 amperes. The only difference is the decay starts is at t is equal to 16 microsecond and not at t equal to 0 microsecond. So we have to do the same time shifting here. So let's start a new time scale, Tc in this case, with Tc equal to 0 here. So Tc equals t minus 16 microseconds. This circuit is the same as a case 3 circuit. The solution is an exponential decay. IL is IL0 e power minus Tc by tau. I can substitute for IL0 and we get this. And it can be plotted. So from 1.04 amperes, it decays down to 0 amperes. This is the steady state of this circuit if you treat it as a standalone DC circuit. And at this point, we are going to turn on the switch again, corresponding to t equal to 20 microsecond. That is the next turn on instant. So let's find the value of inductor current here. So that will correspond to Tc equal to 4 microseconds. So at Tc equal to 4 microseconds, we get 0.851 amperes. I can mark it here. So what has happened so far? We started from 0 amperes. We turned on the switch for 6 microseconds. The current reached 0.648 amperes. Then we turned the switch off. The current decayed down to 0.531 exponentially. We turned the switch on again. The current built up to 1.04 amperes in 6 microseconds again. Again we turn it off, the current comes down. Whenever we turn off, the current exponentially decays. And whenever we turn on the switch, VDC gets connected, the current exponentially builds up. We can continue to do it alternately. And if you do it, you can see that the current goes up whenever VDC is connected, switch is on, and goes down whenever the switch is switched off. This happens alternately. You can see that the solution slowly converges to a steady state. The average current here, if you continue this process and then take one cycle and then take the average, that will be 1.5 amperes. You can continue and check it out. This is the steady state of the power electronic converter. This is the transient of the power electronic converter. Notice that inside the steady state, if you take this turn on interval, the DC circuit is trying to go to 2.5 amperes. It is undergoing a transient actually. But the power electronic circuit is in steady state here when the average quantities in a DC power converter have reached constant values. So as expected, under steady state operation, IL average is 1.5 amperes. You can work it out and calculate this average here. Only thing is here we have just taken a few cycles. In reality, you need to take a few more cycles before it reaches steady state. But even here, you can see visually it has almost reached steady state. So with IL average 1.5 amperes, we can calculate the average of the resistance voltage, VR average, output voltage, which will be average current times the resistance value, 1.5 times 10, which is 15 volts. We have already seen that the DC voltage, expected DC voltage, is duty cycle times VDC, which is 0.6 times 25, which is 15 volts. So that is the direct calculation of the output voltage, whereas the actual process of reaching the output voltage is this. If you build this circuit and leave it on the bench, system is not going to jump to the steady state immediately. It is going to undergo a transient before it reaches this steady state. In this case, in a DC converter, at the steady state, the waveforms are repeated. The inductor current waveform in one cycle is identical to the inductor current waveform in another cycle. It is true in many cases, but there can be cases, particularly with AC converters, AC input or AC output converters, the switching pattern and the AC voltages and currents may not be exactly synchronized, and this may not occur. But in many cases, this will be the case. Here we can check one more thing. As we continue, we can continue these calculations. We can continue to calculate this value, this value, this value, this value, and so on, and arrive at a value of the current here. When enough switchings have passed on, that current can be calculated to be 1.348 amperes. I call that current ILV, corresponding to valley current. There is a valley point, there is a peak point. At the valley point, it is 1.348 amperes. If I take a cycle under steady state and take this current, ILV, the valley current, then that will form the initial current for that cycle. So the corresponding equation will be 1.348 minus 2.5 times e power minus 50,000 Tx plus 2.5 amperes, where Tx is the time scale from that instant. Then I substitute Tx equal to 6 microseconds in order to determine the peak current value, and that turns out to be 1.647 amperes. So from 1.348 amperes, I reach a peak of 1.647 amperes. Now the switch is turned off. The current is freewheeling through the diode. We are assuming an ideal diode. So it's an exponential decay is going to occur. So this 1.647 amperes of inductor current is going to decay down to 0. It's going to tend towards that. But at this point, corresponding to 90 microsecond, we are going to turn the switch on again. So let me find the value of the inductor current at this instant. So I can write the corresponding equation for that as 1.647, that is the starting initial current, e power minus 50,000 ty, where ty is the time scale starting from here. So I substitute that interval of 4 microsecond in order to find out this value. As you can guess, when I do that, I get back the same current, 1.348 amperes. So at the steady state, I start from 1.348 amperes, reach a peak value of 1.647 amperes at the end of the on interval, and then during the off interval, the current comes down to the initial value of 1.348 amperes. So that indicates that we are in steady state here. So I can continue this process. You will find that it oscillates between 1.647 and 1.348. So under the steady state, the pattern is repeated. The average current and the average voltages have reached constant values in this DC case. In the case of an AC inverter or something, the average value will follow the actual AC value for which the converter has been designed. So what is the takeaway here? Just like in the DC circuit case and in any AC circuit case, and the currents and the voltages will reach steady state after undergoing transient in the case of power electronic circuits also. So there is a transient before it reaches steady state. That is number one. Another point is, even when the circuit has reached steady state, in each switching interval, the on interval, the off interval here, the circuit undergoes a transient. The underlying circuit undergoes a transient. This is a speciality of power electronics. In each switching interval, the underlying circuit undergoes a transient, and the power electronic steady state is strung together with these pieces of transients. Another takeaway is, when we analyze a power converter circuit, either as a designer or as a student, we are very often interested in determining the steady state performance, steady state solution of the converter directly bypassing the transient analysis. We will assume that the circuit is somehow reached the steady state and then try to determine the steady state performance directly. We would like to know how the circuit operates under steady state conditions, the current and voltage waveforms at various points in the circuit, the output voltages, the output currents, the input currents, and sometimes even input voltages we would like to determine. We would like to determine the current and voltage stresses of the various components in the circuit. And we also would like to know the boundaries or the limits of operation of the circuit. Inside what operating conditions will the circuit perform as desired? That is also one more thing that we are interested in finding out in a steady state analysis. We may be interested in the transient operation in order to find out how the circuit is going to start. Is it going to start properly? Is it going to get overstressed during starting? But that's a separate problem. That is normally treated as a separate problem. Typically, when we do the analysis, when we understand the converter operation, we are talking directly solving for the steady state operation of the converter. That is the takeaway from this video. Thank you very much. If you find this series of videos useful, and interesting, please consider subscribing to this channel and also clicking the like button. Thank you very much.